which includes both rational and irrational numbers. Now we can represent the set of real numbers using the number line. So we have a number line like this, and points on this line represent different components of the different real numbers. If we combine two number lines, then we have a space which is defined as R2. So the dimension is 2. In that case, we take a point on the x line, this horizontal number line, and a point on the vertical number line, and the combination of these 2 points will give us x2, y2. So any point, so instead of being on the number line, we will have points on anywhere over here, length
Sir,
into
sorry.
breadth.
So
Yeah.
sorry to interrupt you, sir. I cannot see your presentation.
Okay. What about the other people?
Can see
So
it,
we can
sir.
see. Sir, it's
Fine.
visible.
Sir, I can see.
We can see.
We can
Sir, we
see,
can.
sir.
Okay, I'll just stop presenting and then uh, do it again. Okay, let's see. Entire screen.
Yes, I can see it right now. Now I can.
Okay,
Thank you so much, sir.
yeah, my pleasure. Okay, so instead of a point on the number line, where we have only one dimension, we now have two dimension, length and breadth, you can see. And therefore, a point has to be defined using not one number line, but both of them. So we have to give the references using both the number lines. For instance, this point is x2, y2. And obviously, we can expand this further. This is a real space within 3 dimensions. Unfortunately, this is as far as we can go. R4, R5 is theoretically possible, but we cannot draw it. Okay. Then we have defined the concept of intervals. We define two bounds, A and B, which when A and B belongs to the set of real numbers, and all points between A and B are within the interval. Now, as I've said before, that the interval can be of primarily of 3 types. It can be closed, in which case both the bounds are included within the set. And we represent this in terms of greater than equal to. The other extreme is open interval, where the bounds are not included within the set. So instead of greater than equal to, we have strict inequality. And in between, we have uh, two types of boundary, both of which can be called half open or half closed or semi open, semi closed interval. In that case, only one of the boundaries are taken within the set. For instance, in the first case, only the lower bound A is included within the set. Here, only the upper bound is included within the set. So we define this in terms of a combination of weak inequality and strong inequality. So Interval is a set of points within two boundaries, and the boundaries define the limits of the set. We can also have unbounded set, where the set continues indefinitely. Now, if the set is closed, that is, the boundaries are within the set and it is obviously bounded. So, if the set is closed and bounded, we call it a compact set. So, what is a boundary point? Well, I mean, obviously, or intuitively, you can say that a boundary point is at the margin, at the end of the set. Now, technically, we can define it by saying that suppose we define a neighborhood, a very, very small neighborhood around, let us say, B. So we take a point B and we find out, we take a neighborhood. So how can we take the neighborhood? It can be either slightly less than B or it can be slightly more than B. So that means B minus E epsilon or B plus epsilon. What is important is that if we take points defined like this, B minus C, B plus C, then some of these points will lie inside the set or inside the interval. Some of the points will lie outside the interval. In this case, we have taken the upper boundary. So B minus epsilon will lie inside the set. B plus epsilon will lie outside the set. But suppose we take the lower boundary, we can also define a neighborhood around A. So in that case, A minus epsilon, this will lie outside the set. B plus epsilon, sorry, A plus epsilon will lie within the
Inside
interval.
set.
Yeah. On the other hand, what is an interior point? If we take the neighborhood and the neighborhood is sufficiently small enough, then it will contain points only within the interval. See, if epsilon is very large, let's think of an interval A and B as uh, 0 and 1. So let's take a point in between, 0.5. If you take an interval like say 10, then obviously points will lie outside the interval. What I'm saying is that we can find out an E which is so small that any point, if we define the neighborhood using epsilon, it will lie entirely within the interval A to B. For instance, if we take a neighborhood of point, let us say point 0.00001. Okay. So in that case, if we take, let us say, zero point 0.1, if we subtract epsilon, it will still be between 0 and 1. If you add epsilon, it will still be within 0 and 1. Then we defined convexity. If we take any two points in the interval, say x0 and b, all points on the line segment must also lie within this interval. So formally we say if lambda lies between 0 and 1, closed boundary, then we can define x. X is a point within the boundary. X is defined as lambda x1 plus 1 minus lambda x2. So if it is a convex set, x will always lie between x0 and b. So if we manipulate this a little slightly, we can define this as x2 minus lambda x2 minus x1. So basically what we are doing is x2 minus something, we can write this as theta. So x2 minus theta, when the value of theta can be, it varies. Okay. Now what is the highest value of x? See, if this part, the second component, increases, we are subtracting more and more from x2. Okay. So that means suppose lambda is 0. In that case, we will just have x equal to x2. This will be the highest value. And what is the lowest value? Again, intuitively. See, varying, by changing the value of lambda, we can move along this number line. We can either approach b or we can come down to x0. So as lambda increases, we move towards x0. We move like this. As lambda decreases, we move towards the maximum value. So if lambda is equal to 0, we will have x will be equal to b. If lambda is equal to 1, x0 will be equal, sorry, x will be equal to x0. Okay, so this is just the repetition of the definition. And this is the geometric part. As I've told you, this is not a convex set because points like this is outside the set. So we had said that these are all examples of convex sets, and these are, on the other hand, examples of sets which are not convex. Okay. So is this clear, everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
Okay. Then let us define distance. We have, if we go back to the number line, then we have 2 points A and B, and let us assume that B is greater. So the distance between them will be simply B minus A. So if we have 2 points, let us say 4 and 7, the distance will be 7 minus 4, 3. Now here we are talking about a one-dimension space, the number line. If we go to R square, we have to think in terms of what is called Euclidean distance. Please mute yourself. Someone has unmuted. Okay. Okay. So here, if we take 2 points A and B, what is the distance between them? Sorry, I've made a typo over here. It should be 1. A1 minus B1. So here, the Euclidean distance can be defined in this way. We are just using the Pythagoras theorem. And if you want to think of a general, more general terms, when we have an n-dimension space, then it is simply summation of ai minus bi whole square. Okay. Now, if you have downloaded Hoy's book, you will see that I have been primarily teaching from Hoy, Uh, Now, page 35 to 39 contains some definitions. So, I'm not going through the definitions, it's basic, but I would like you to go through the definitions and also try to solve the problems given in the chapter. If you have any problems with the definitions, we can discuss it in the next class. Okay. Now we come to the next part, which is functions. Now functions can be of one variables or it can be of multiple variables. But in the first semester, we are going to focus on functions with one variable. So we have two sets, A and B. The members of A are supposed to be given by x1, x2, x3, and so on. And B is given by y1, y2, so on. So we can define a rule that transforms each element of A. That is, we take a particular x and this will be transformed into one or more element of B. So mapping is, this is called mapping. So mapping is the rule which leads from x to y. So given x, we can get y. Here, A is called the domain, while B is called the range. It is also called the core domain. And Y is called the image of X. So we can have, let's look at into this a little bit more carefully. So suppose we have a real valued function of a real variable X. X is a real number and its domain, the set of all X's, is given by a set D. So a real valued function is defined as a rule that assigns a unique real number to each real number x in D. So that means if I take a real number x, the function will suggest a rule such that if we apply it to x, we will get a corresponding y. So if we apply it to x1, we will get a corresponding y1. The set of all possible value fx is called the range of f. So functions are a very special type of mapping. I'll come to the definition a little bit, or I'll come to the distinction later. But right now, let's proceed with the definition of function. So the function is represented as y equal to fx. Y is called the independent variable, x is called the dependent variable. In economics, x is referred to exogenous variable, y is called the endogenous variable.
So I have a doubt.
Yes, please.
So why is x the dependent variable?
Sorry, it's a typo. Sorry.
That's okay, sir.
Yeah. Okay, just give me one moment, please. Okay. So y is called the dependent variable, x is the independent variable. Now, the function f is called increasing if it satisfies the following properties. If we take a two values, two x's, x1 and x2, x2 is greater, then the corresponding y's, y1 and y2, y2 will be greater than or equal to y1. It will be strictly increasing if y2 is strictly greater than y1. Linearity, well, if we plot it, we get a straight line with A as the intercept and B as the slope. So in economics, uh, we deal a lot with straight lines, consumption functions, demand functions, supply functions. They need not necessarily be nonlinear, but we find it more convenient to use or think of them as linear functions. Now, if you think of the properties of the functions, okay, they can be one to one or many to one. Let's come over, look into this diagram. See, here we can see that we have a particular x1. This leads to a unique y1. On the other hand, if we go back along this line, y1 is also associated with a unique x1. Is this clear? This is a one-to-one function. One-to-many is that x1, we have one x1, this can generate multiple y1s, multiple values of y. So this is, let us say, y11, this is y12. We have another x2, this generates y21 and y22. So if you are given y, can you find out the a unique x? And the answer is yes. But given x, can we find out a unique y? The answer is no. Okay. So just as we have one to many, it is also possible to have many to many. Sorry, many to one. Let's see. Sorry, there's a mistake over here. Okay. This is a many to one functions, many to one mappings. As you can see over here, this is a, in fact, let me change this. Let me use the word mapping. Okay. Here you can see we have two x's and both of them are generating the same y. So we have many x's, the y is same. Okay. So given x, can we define the corresponding y? The answer is yes. But if we are given y, do we know what the x is? The answer is no, because it can be x can be either this or x can be this. Now let's go to many to many.
Sir, I had a question.
Yes, please. Or just
Sir,
wait for
could
a
you
moment.
please?
Just wait for a
Yeah.
minute. Yeah. What was your question?
Sir, could you please give an example of one-to-many function?
One to many function.
Yes, sir.
Uh, okay. I'll just
So can I answer?
know this. Yeah, you can.
So is x equal to y square a valid example in this case?
Sorry.
Is x equal to y square a valid example in this case?
X equal to y square. No, here what you're doing is you have defined y as the dependent variable.
Okay,
No, I think
right.
it is better if you look at it. Okay. Look at this. Okay, we have the x's over here. So over here, you can see that if you take a particular x, if we take x over here, it generates a unique y, right?
Yes, sir.
What is this type of mapping called?
One to
Is
one,
it one
like
to
if
one mapping?
This is
x generates
1
one,
is to
yeah,
1. Yeah.
one.
So if we shift x, it will generate only one value of a unique value of y. Over here, in this case,
It's still
It
one
is
to
also
one.
one to one
One to
mapping.
one, sir.
Still one
it's
to
still
one,
1
sir.
to 1. The only difference is previously it was an increasing function. Now it's a decreasing
Decrease.
function.
Decreasing function.
Okay, right? So if we take this, it's not well
Many
drawn,
one.
but you can
It's
understand.
many to one
So
mapping.
it's many one
Many
function.
one, many one.
Many
Yeah,
one
Many
function.
to one.
yeah,
Yeah,
it's many
like
to
yeah.
one mapping. You have two x's, you get only one y. Okay, now What is
It's
this
one to
type
many
of
mapping.
mapping?
It is one to many mapping.
It is one
Yes,
to
sir. One to
many
many.
mapping.
Oh, yeah, it is one to many mapping.
Yeah, many to many. Hmm, let's see. See over here, the same x is generating three values of y. So it is a case of
So one to many mapping.
one to many. But again, if you okay, let's keep this over here. And sorry. But if you take, let us say, a point like here, we have two x's but the same y,
It is
right?
many to one mapping.
Yes, sir.
Yeah. So,
Yeah,
so
it's many to many then.
yeah. So this type of mapping is called many to many. Okay.
So could you explain this once more? The
Okay.
last one.
Many to many. Okay. See, depending, see, many to many, it doesn't mean that all the points will be unique. Okay. Uh, let's come to over here. One to many. It doesn't mean that all points will be like this. See, look at this point. This is one to one. So you have at least one point, one x, which generates two values of y. Right? We call this one to many. We don't mean that all x's will generate multiple values. For instance, just think of this. Okay. Now let us take, see, over here, we have the same y being generated. But if you take a point like this, right? In that case, well, not exactly this. Let us say something like this. Is the same function, but here x is generating a unique y, which is the maximum. See, here is the same. At this value of x, we have a unique value of y, which is the minimum. But if we take a different value of x, right? If we take a different value of y, it can be generated by two x's, this and this. See, this value of y will be generated by another x. If you look over here, x is generating this value. It is also generated by this. Okay. So we are not saying that all points will be one to many. One to many mapping means there will be at least one point like this. We can also have simply one to one also within these. Okay. Here also similarly, we can have a point which is 1 to 1. We should have at least two x's which generate the same y. Okay, or the converse, we should have at least one y which is generated by two x's. But for the remaining cases, we can have one-to-one mapping. Okay. Similarly over here,
Sir,
yes.
I can't see the scheme.
Okay. Better? Can you see it now? Okay, I think she's just cracked out. That's why she couldn't see it. Okay. So is the point clear? What I'm saying is one-to-one mapping, all points must satisfy one-to-one. But if you have one to many or many to one or many to many, we can have some points which for which we have one-to-one mapping. Here, for instance, you can see this is a case of many to one. This is a case of one to one. This is a case of many to many to one. And we can also have a case like this. Okay. So we have the same x generating different this y, but this y is being generated by different x's. Okay. Now, as you have seen, we have four possible types of mapping: one-to-one, one-to-many, many-to-one, and many-to-many. When we are talking about functions, only one-to-one mapping, this is a
So I have a
function.
doubt.
Yes. Or let me finish this, I'll come back to you.
Okay, okay, sir.
This is not a function. Many-to-many is also not a function. Many-to-one is also a function. Okay. So if we have one-to-one or many-to-one, these are examples of functions. But if it is one-to-many or many-to-many, these are not functions. These are simple mappings. Yes, what was your question? Yeah, I think someone had a doubt.
Yes, sir. I was going to say that the mapping will not be a function because every image is Hello, sir.
Yeah.
Am I audible?
Yes, yes.
Yes, sir.
So you
So,
wanted to say that all mappings are not functions. Yeah,
yes, sir, because
correct.
many to many.
So as you can see, yeah, two of them only are functions. So as you can see, this is a function. This is also a function, but the blue line, or if we take a line like this inverse of C, these are not functions. Now the other definition is onto and into function. This is an onto function. Look at it carefully. I will then show you what is an into function. This is an into function. What is the difference between onto and into?
Sir, in onto, I think range is equal to codomain, and in into range is a subset of codomain.
Okay, this is an onto. What is the range?
So I think the arrows in the box, those values will be the range, and the entire box
Okay,
is the
let's go to the
range.
definitions. Range and codomain is basically the same, right? The set A or X, that is the domain, and B is called the range or codomain.
So for onto functions, I think each element of the range, that is y, should be connected to the domain. But for into functions, there should be at least one y in the range that is not connected to basically the input set.
Yeah,
Sir, for an onto function, every element of the codomain has a pre-image in the domain, and that
exactly.
is not so for the into function.
Yeah. So if we take a y over here, every my y has been generated by at least one x. In case of an onto function, all the x's which have generated y's will fall in the set A. But over here, the real numbers which have generated y, some of them will lie outside the set A, outside the set, outside the domain. Hmm. Can you give an example of an into function?
Yes, can I answer? Am I
Sure.
audible?
Yes.
So can we make a function from a set of whole numbers to a set of natural numbers? So 0 is included in the range and it will be included in the domain.
No, but no, I don't get you. How does it become an into function?
For
So this is
example,
the, let us say this is the set of, is this whole numbers or natural numbers?
so the natural numbers.
Okay, so this is 1, 2, 3, so on.
Yes, yes.
And what is the domain?
The
Mean is the whole number set.
Whole number 0, 1, 2, 3. Okay.
Yes.
So what is the
And the
mapping
function.
rule?
So y equal to x if we plot. So we won't have 0 in the range.
No, it is exactly the opposite. 0 should not be over here. Okay. We should
Yeah,
have a,
right. So I was confused. Yeah, exactly. I was confused.
Sir, can we take y equal to x plus 1? Where the domain is the set of whole numbers and the codomain will be the set of natural numbers.
this is whole numbers. So your 0 plus 1. This is natural numbers. Okay.
Yes, sir.
Okay. So in that case, it starts from 1.
Yes.
So if it starts from 1, you will have a 0 which is over here.
So then we can take x equal to y plus 1.
X equal to,
Y plus 1.
no. You have to, you're defined, no, it has to be y equal to something.
So y equal to x
Y equal
minus
to,
1 then.
y equal to
X
x
minus 1.
minus x minus 1.
1.
Yes, but what is the lowest value of 1 of y? It is 1.
Yes, sir.
How do you get this? 2
Sir, if
minus
we,
1.
yes. Sir, I am considering x to be the set of whole numbers and y to be the set of natural numbers.
Okay. So this will start from 0, 1, 2, 3, so on.
Yes.
Right?
Yes.
This is 1, 2, 3, so on. Right?
Hmm.
How do we generate 1? 2 minus 1. So
Yes.
x is equal to 2.
Hmm.
We have 0 and 1 over here, which doesn't have any image.
Yeah.
What we need is a pre-image, which is not over here. Think
Yes,
of
sir.
9. I'll give you some numbers. Let us take these numbers. 4, 9, 16, 1, 1, 4, 9, 16, 25.
Sir, x
So
equal to
for
y
this,
square.
So y equals to
so
x
y is
square.
equal to x square. And the domain is a set of natural numbers and the codomain is a set of integers. So y is equal to x square will be valid for into function.
Yeah. So if it is 1 over here, we are going to get 1 over here also. Right? But 1 can be generated by minus 1 also, minus 1 whole square. So it is something like, oops, it is something like this. This is minus 1, this is plus 1. This is minus 2, plus 2. Both of them are generating 4. Okay. Now, when we are talking about pre-images, then one possibility is, can we start with y and find out what is the value of x that has generated y? Now remember, we want to generate a unique value of x. Is it possible y equal to x square? Is it possible in this case that I'm giving you a value of y, you have to tell me what is x?
Yes, sir.
Okay, 25. Y is equal to 25. What is x?
5
So
plus
5.
minus 5
We take the inverse of the
No,
given
I had
function.
taken
plus
minus 5.
minus 5 plus
Plus
minus 5.
minus 5.
What I want is a unique value of x. Can you give me that?
No, sir.
Exactly. It's no. Not very audible, but clear. Suppose we take x minus 1. Suppose y is equal to x minus 1. And y, the value of y is 6. What is the value of x?
So
Seven.
7.
7.
7, sir.
So
Yeah,
everyone
that
will,
is possible. Yeah.
yeah.
So in this case, it will be possible.
In
Yes,
this
sir.
case, it is
It's
possible.
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 Now let's just go back, right? In this case, if you look over here, or the orange one, these are examples of functions, right? If you're given the value of y, any value of y, can you tell me what is x?
No, sir.
No.
So there will be two different values of x for a
Yeah,
particular y.
yeah. Except for the maximum or minimum, you will always get 2 points.
Yes.
This and this, this and this. Yeah. So, what type of mapping is this? Many to one?
Yes, sir.
Yes.
Yes, sir.
Achha, geometrically, can you think of a function where you can always get x? Think of this.
A line that is parallel to the y-axis.
No, not parallel.
A downward sloping
Any
straight
straight
line.
line, positive,
Downward
negative
sloping
sloping.
or
Upward sloping. So any
Upward
straight line.
sloping.
any straight line.
Yes, sir.
Uh, Suppose it is, let us say, where is the shape? This one. This is not a straight line. It is not a linear function. But if I give you a value of y, can you give me a unique value of x?
Yes,
Yes.
sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah. Yes?
Yes.
Okay. We can also make it negatively sloped, right? Okay. What type of mapping is this? The red lines.
1 to 1, sir.
1 to
One-to-one
1.
mapping.
One.
1 1, sir.
So, what is the answer to this?
So for 1 functions.
In case of one-to-one function.
Yes. So, if you have one-to-one functions, then we can, or rather one-to-one mapping, we can generate what we call inverse functions. So y equal to x minus 1, it will become x equal to y plus
Plus
1.
1.
Yeah. So basically what we are saying, both has to be 1 is to 1. The function and its inverse, both has to be 1 is to 1. Okay. Plus function. Okay, and this is what we called a composite map, very complicated. So we have over here a rule f. So if you are given x1, you have you apply the rule and you get y1, okay, or f of x1. Then you apply another rule which will give you z1. So you can think of, let us say, let us suppose we take log. So we define y equal to log of x. And we define the g function as square. So in that case, what is z? Z is log x whole square. We can directly go from here x to z, or we can first convert it into log, then we can take the square. So these are called composite maps, and of course you realize that we can extend it even further. So we can have a series of transformations. Linear functions, if we can, obviously any function or any mapping can be graphed, and if we generate a straight line, we call it a linear function. In case of a linear function, the slope is constant at all points. So we can have positively sloped, negatively sloped. These passes through the origin, intercept is 0, but here the intercept is uh, has a non-zero value. And these are nonlinear functions, a function that does not generate a straight line. Examples: quadratic functions, rectangular hyperbola, power, exponential, and log functions. Now I want volunteers. I've told you that I'm teaching from Hoy. I want the first 4 students. Uh, Let me see. So I want the first 4 students to prepare slide. The first student will prepare a slide on quadratic functions, second on rectangular hyperbola. Okay. So Deepika Paul, are you there?
Hello, sir.
Ahana Vishar? Yes. Deepika Paul?
Sir, yes, I am here. Yes, sir,
Okay.
I am here.
Ahana Vishar? Okay. Sneha Sutradhar?
Yes, sir.
Devo? Okay. Devoparna Mojumdar? Devoparna? Okay. Audit Shaha?
Yes, sir.
Akankha Shaha?
Yes, sir.
No.
Yes, sir.
Okay. So Deepika, you will prepare on, let me see, quadratic. Uh, Ahona will prepare on rectangular hyperbola. Audit, right? Power and exponential, and Akankha on log functions. So you'll prepare 1 or 2 slides, and in the next class, you will discuss these 4 cases at the beginning. Okay? You will be the
So,
teacher. Yes,
sir, could
please.
you share your presentation again? So it's again showing the video is not being shown. The PPT is not being shown.
Yeah. Can you see it now?
So just a second. So no, sir.
নাও না, আমার ফোনটা বাইরে আছে। Sorry, you can't see it. Okay.
Excuse me, sir.
Yes, now.
Yes, I can see. Thank you
Okay.
so much.
So quadratic functions, rectangular hyperbola, power exponential, that's the third slide, and log functions. I'll also post it on the message. By the way, when I post it, are you getting any corresponding messages? If I post
Yes,
in
sir,
the
we get a
Yes.
notification.
okay, okay. So all each of you will prepare using Hoist book one or maximum two slides on your given topic, and you will be the teacher. Okay. So you can see which of them are
Sir, when is
functions.
our
And
next
now,
class?
uh, next class, I'll tell you at the end, but you will get plenty of time. Don't worry. Okay. Which of them are functions? You know that. Acha. Next is, you remember that I told you that you're mixing it up. One of you said that x is equal to y plus 1, something like that. See, sometimes we can have what is called reverse causality. For instance, mm, let us say that we what can okay, let us say that your income increases. In that case, will you purchase more of a commodity?
Yes, sir.
It
Or
will,
we can
Yes,
also
sir.
save
Yes,
it.
sir.
it will
Yeah,
depend whether the commodity is a inferior good or a
Normal good.
Normal good.
normal good.
yeah. Let's think of it in general. So in general, what happens is as your income increases, your demand is going to go up. You want to purchase more of different commodities.
Yes.
So here you have a particular direction of causality, income to demand, right? We believe that income causes demand. But in some cases, for instance, think of health and economic growth. Which causes which? Does health cause growth or does growth cause improve health?
Both.
Both. Here we have reverse causality. A
Yes.
more healthy workforce means growth will be faster. But if growth improves, per capita income goes up and people spend more on health.
Health.
Okay. So it's a case of the egg and chicken argument. X causes Y, Y also can cause X. So in those cases where we are not sure what is the direction of causality, or we can have both types of causality, we can write the function in this form. Instead of writing y as a function of x, we write fxy equal to 0. This is called an implicit function. Okay, so this is the end of today's class. In the next class, we'll start off with the power functions and so on. And then I'm going to discuss some concepts related to slopes and elasticity. Okay, then. Um, One issue was when is the next class? Monday, I have a class with you, but I mean, if you can we hold the class in the evening around 5?
Yes, sir, no problem.
Yes.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, in that case, I won't change the class. I'll take it on Monday, Monday 5 o'clock. The second is regarding your G. Uh, the head wants to speak with you, but before that, just I think there was a misunderstanding. Uh, what we wanted to convey is that, see, uh, when we studied economics, math, science, statistics was supposed to be a royal combination. Okay, and we had very, but remember two things. We had very rigid combinations. One, if you don't take stats, you have to take pol science. Secondly, if you don't take maths, in that case, it will be a BA degree, not BSc. Now, under the new regulations, if you have economics, whatever your past subject is, you're going to be a BSc graduate, not a BA graduate. Okay. Ideally, I'll just stop presenting. So, ideally, if you're confident, you should take maths. You may also take statistics. Statistics, if you take uh, whatever is needed from an economist, will be covered in our courses. So stats you can drop. Maths, if you're confident of your mathematical ability, then only take maths. How many papers you take, it depends on your level of confidence. Don't try to take a maths paper and then fail. Okay. If you take maths, our suggestion is go for differential calculus. That will help you. If you take algebra, that will also help you. Integral calculus, we don't require that much. It may be difficult for you. Okay. So if you are confident, then only take a maths paper and take a maths paper. The first maths paper you should think is differential calculus. And the second maths paper that you should think is algebra.